From Imperial College London, welcome to this special lecture vodcast.
It's a very great honour to be standing here giving the Gabor lectures. Gabor is one of those people who, yes, he won a Nobel Prize, but that paper in Nature on holography is really one of those remarkable pieces of work to see how somebody could understand wave theory to the extent of putting that down. And it's also an amazingly brief little paper. And I thought I would just start with the global challenges of the 21st century by referring, if you don't mind, to my own work on electron holography. Back in the early 90s, we decided that it might be an idea to look at the fact that we understand, of course, that electrons have wave properties, and therefore we could extend Gabor's ideas to atomic resolution. And so we were using low-energy electron diffraction at that time, but we could also collect Auger data. Now, the idea behind this is that the atoms on the surface are themselves the source of the electrons that are radiating nearby atoms. And so you could use that as a means of going back to Gabor's transform, his holographic transform, mathematically use that to convert that for electrons. And we did actually have quite a good result out of it. It's actually this paper here, which was atomic resolution holography in practice. Iodine atoms on silver, and I'm just going to then show you the results. There's the hologram here. This is electron pattern. I stress again, if you try to do a direct inversion with a system where each and every atom is a source of electrons, you get a rather confusing real space picture. So what we did instead was start from real space and invert it. So these are our calculated images, and I hope you can see that this image here is a fairly good representation of that, and from that we deduced the sites preferred by the iodine atoms on the silver surface. So did that idea last? Well, actually no. The resolution, although it looked rather stunning to do atomic resolution holography, the resolution in terms of interatomic spacings isn't as good as we're getting from a full multiple scattering theory analysis. And that's another way of paying tribute to Imperial College, because one of your great stars, John Pendry, I don't know if he's here. Well, well, John and I worked fairly closely together some time ago, and he was the one who finally put together multiple scattering theory for lead analysis, and that is the tool we're still using. It's more accurate than this one. Right, what I'm really going to talk about now is the challenges of the 21st century as distinct from the challenges that we faced through the 20th century. So what lies ahead of us that will be distinguishable from what we've been doing through the 20th century? And this slide contains the rest of what I'm going to be talking about. So really, it's questions around population growth, disease, water provision, energy sustainability, and of course what we're doing to the atmosphere. Just taking sustainable development so that I can deal with an important economic tool to start with. We can actually move away from the norm of competition, if you like, that Premier League of countries in terms of GDP growth that The Economist publishes every week, and that I always open to first of all when I look at The Economist, GDP growth per country. The suggestion is that as long as your metric is GDP growth, we will all try to aim for the maximum GDP growth. The alternative would be to use national wealth and the growth in national wealth as a target through the 21st century. I'm using Partha Dasgupta's quantifiable notion of wealth of a nation here, which is that we need to assess our productive base in terms of the Manufactured capital, that would be all of our infrastructure, the building we're in now, the roads, the airports, the factories, the schools, the universities. Human capital, that is the level of human skills in a given society and how that can contribute to the wealth of a nation. The natural and environmental capital, and here of course I'm referring to, for example, natural resources such as oil or gold, and if you count in your natural resources as an asset and you use those natural resources, you've got to make up for that by reinvesting into your manufactured or human capital. Now, that's a very important difference between Dasgupta's wealth of a nation and GDP growth. So those oil-rich nations that are approaching the end of their supply ought to have been reinvesting in other means of wealth generation if they're going to manage that. But of course, importantly there, we also have environmental capital in terms of the state of the environment. And we're now beginning to cost in dealing with acid rain and so on by actually internalizing the external cost. So we are beginning to do that, but we still haven't accepted a quantifiable measure. And then we've got institutional and cultural capital. So add all that together, you've got the wealth of a nation. If we can just agree on a way of quantifying that, we would have a much better totem pole to be climbing up than simply the current GDP growth measures. So I've now dealt with sustainable development in the economic terms that I would like to, and I'm going to move on to population growth. Now what we see here is the spectacular shortening through the 20th century of the rate at which of the timescale over which we have added 1 billion people to our world's population. So first billion on the planet was reached around 1800. The second billion took 123 years, and we reached that in 1930. But you'll see that by the middle of the 20th century, we had lowered the number of years taken to add 1 billion down to 12. Now, I'm going to suggest that that was a massive production emerging from science, engineering, medicine, and technology in the 19th and 20th centuries. In other words, what this reflects is lifespan increase in the human population. We turn to the beginning of the 20th century when lifespan around the world would be in the region of 45 to 50, and today, with the exception of one continent, lifespan is in excess of 70. So what we see is that we complain about population growth, but it's a direct consequence of providing better conditions for human beings to survive longer. Now, of course, I need to analyze population growth in a little more detail, so let me give you the stages of demographic transition. We need to understand this if we're going to talk sensibly about population growth through the 21st century. And what I'm presenting here is a neat little model that tends to encapsulate country by country how population growth changes. We start from a period, I've pushed the wrong button again. We start from a period before we introduce advances in science, medicine, technology, clean water, hygienic conditions, etc. And so we have a high mortality rate, so the death rate is high, and we have a high birth rate, and that gives us a steady state in the population. Both numbers, birth and death rate, are high. And so typically a female fertility rate here might be around 7 to 10. And this, if we extrapolate back in our history, would be true. Look at any country and you'll find that. Then we get sudden improvements due to the advent of these advantages I'm just talking about. And the impact is felt immediately in a lowering of the death rate. But in the meantime, women are still having the same number of children. Now, if you look at the analysis, it's almost inescapable that women have had enough children at any point in time that roughly 2 survive into maturity. And of course, today, that would mean that our female fertility rate would be 2.1 to give us a stable population. As a matter of fact, in this country, we're at 1.8, so we've overshot. Women are not producing quite enough according to that little principle. But nevertheless, the idea is that roughly 2 per woman were into maturity. And as we realize that more and more of our children are surviving, we then go through this period of rapid growth rate where there's an inequality between birth rate, still high, and death rate. And of course, over that period of time, because birth rate is still high, you're producing more young girls who become women who want however many children per person. So that continues for quite a span of time. But then we all find, whatever mechanism is used to do this, often it just happens socially, that the birth rate, the female fertility rate drops, so the birth rate drops, and we reached another roughly steady state. And that's roughly where the Western world is now. But interestingly, as you travel around the world, you find that it's happening all over the world, with the exception of the African continent. And in the African continent, it's quite patchy. Right, so where are we in terms of, for example, South America? Roughly 2.25, varying a little bit from one South American country to another, but remarkably not that much. If you then go to Italy, it's surprising. Italy, Spain, Portugal, 1.25 around. Germany, for a long time, has been down at about 1.2. So these are the countries where aging population becomes one aspect of the 21st century challenge. So we just signal that as one of the challenges that I'm going to run through. Let's just illustrate that in terms of the anticipated population growth through this century. So we're now at 6.4 billion. If you look at this curve, we can say with some certainty that by 2028 we will pass 8 billion. We're slowing down in terms of adding a billion years. We're down to 13 years, and remember the smallest time was 12. And then it'll slow down even further until we reach mid-century. It's going to be around 9 billion, and now we are extrapolating a little far forward, but it does look as if female fertility rates are coming down faster than most of the population growth people had anticipated. So we can anticipate a stabilizing somewhere around 9 billion by mid-century. There's the big challenge. We have an additional 50% anticipated population by mid-century, and all of the questions that I'm now going to raise flow from that statement. Just, of course, now this is the consequence of the differential between growth rates in different countries and different continents. Is the more developed countries have more or less stabilized, and the growth is in the less developed countries, and within the less developed, it's the least developed where growth rate is highest. Let's just look at, I think the next slide is really quite remarkable. Different countries with totally different cultural and economic patterns, nevertheless seeing a really dramatic fall over the period shown here, in green 60 to 65 and in blue 2000 to 2005, fall in the female fertility rate. In all cases, up there at 5 or 6 at the beginning of that period, and then 40 years later, down into the stable level of 2.1, where population growth is 0. So take China with a one-child family, or take Mauritius with no particular policy on this. And you see very similar outcomes. Now, I've chosen these countries fairly carefully there, and in particular, I've left out the African continent. So if we just take Africa, their population growth rise is still 2.4% per annum, and this means that the 49 least developed countries will triple in size during the next 50 years. Triple in size. That 2.4% doesn't sound like a lot, but if you take that over an extended period, you can see from the doubling rate what the outcome would be. Well, of course, if we want to bring that under control, it's quite clear from past practice that in addition to medical and hygienic conditions being available, that empowerment of women is absolutely critical in that process. So the one common factor that tends to emerge is the education of women and the availability, particularly to women, of contraception. So as we move forward extracting what policies are required for governments, that's what the British government is now supporting to assist this process. Right, now let's look at the impacts. Can the world really feed 9 billion people? We've had the first agricultural revolution, the green revolution in India, which has transformed India's ability to provide food, and very much driven by the scientific community in India, developing modern plants that were capable of yielding much more efficiently, yielding crops than the older crops that were used before. So plant biology has played an absolutely crucial role in India's capability of feeding its own population. If we then ask, can there be a second revolution? Well, we've already seen a second agricultural revolution emerging with new technology again playing a key role. The net result of all of this is that we need another spurt in food growth efficiency. I think that's certainly on the cards. So I don't think in terms of the capability of the food production process that there is a real challenge. I think it will be managed, the technology will pull it through, the economics will pull it through, so that is something that is doable. But the real question then is, will the food be grown where it is needed, or will the people who can't get hold of the food have the wealth capability to buy it from the people who are producing it? In other words, and this is going to be a common theme as it emerges, the question is one of distribution and wealth. So these are going to be the key questions as we move forward in time. A major complication on food supply is climate change and its impacts, and I'm going to come to that in a moment. Right, the second is impact on health. Well, first of all, if we just look at the population growth impacts on health, this is a very severe problem. Where we see high population growth continuing, then factors such as maternal mortality, infant mortality, are really linked right into high population growth. In Indonesia, detailed analysis has been published showing that 60% of births in that country, where female fertility rates were still high in the early 90s, had at least one of the 4 risk factors for poor health prospects. And just to move on from that, the issue of Africa really has to be pulled out from the rest of the planet. If we take life expectancy again as a measure of well-being across the planet, we find that around the world, as I say, 65 to 70 is predominant. In most of the developed world, we're now talking about 75 and upwards as we move forward in time. But in Africa, 45 to 50, in much of Africa, and in sub-Saharan Africa, 40 to 45. So we're talking about a massive differential. There are real challenges and stresses within Africa: HIV, AIDS, malaria and TB, level of education, questions of governance and corruption, agriculture and productivity, and weakness in science and technology. And it has become rather unfashionable to point this out. And our aid process to Africa has tended to ignore the fact that if we are going to sustainably aid that continent, regular food aid is not necessarily the way that's going to achieve that. My measure of sustainability here would be, if I stop tomorrow, what have I left in place that will continue? if we provide assistance in the educational system, and here I mean holistically, not just primary school education. One aspect of the Western focus on primary school education is that the number of children in primary schools is now much, much greater than it was before, because we didn't provide for a mechanism that would increase the number of teachers. So education has to be attacked holistically all the way through, from primary school to secondary school to colleges of further education to universities to institutes that have the capability to pull excellence through the whole system. So my exemplar of that would be the Indian Institutes of Technology. The average number of applications, Richard, your number here is high, but a typical IIT in India, the number of applicants per place is 900. So what we have then is 900 aspirants who want to get into the elite institutions. That pulls up the educational system. The other 899 get into some very good universities. So it's assisted the whole process. And that is felt all the way down to the level of education in the primary schools. Now, by focusing on primary school education and food aid, we have completely missed the trick. What Africa needs for sustainable wealth development and wealth creation is to develop its skills base, particularly in those areas which pay back in terms of, for example, clean water provision and hygienic conditions. Civil engineers. I've got a lot to say, but I don't want to stay on this topic, but let me just say it. If we took a team of civil engineers that could put clean water and hygienic conditions into a city the size of Sheffield, and if we could do that every week in Africa, we'd be busy for 20 years with that team. We're not going to do that, and it would be silly for us to do that. What is demanded in that equation is that Africa has the capability for producing its own civil engineers that can sensibly run that program forward. Right, so I think that's enough on Africa for the moment. Fresh water is, I don't think it's me. Fresh water is the other big issue as we run through this century. This is a very schematic figure, but nevertheless it contains the element of the problem. So what we suggest in this figure that the actual amount of fresh water is, let's say, constant as we move through this century. So rainfall may change in terms of where it happens, but let's say the average is much the same. And at the same time, human beings pollute water, so the available water after pollution loss is a falling amount because of the rising population. So the question then is just one of where do these two curves cross, and what are the challenges associated with that? So here we have a problem that we're not very focused on, which is cleaning water, generating fresh water. By mid-century, this becomes probably the biggest challenge we're going to be faced with globally. Now, I say by mid-century, and by that I mean on average globally. So we know there's lots of seawater out there, and we can desalinate it. The question is, do we have to wait until the cost is such that fresh water provision becomes so challenging that we're prepared to pay for the current cost of desalination? Or do we need some brilliant scientists to develop a much more economically viable way of developing clean water from contaminated water or salt water? Now, of course, that would assume that every country was faced with the same challenge, and that, again, as with food, is not the problem. If you take I am an African, by the way, if you're wondering why I keep going back to that continent. But Africa, again, is an example of this. The current conflict in Darfur is arguably a conflict associated with water provision because they are faced with annual crop failures. And when people are faced with crop failure, they tend to move to areas where crops will survive, but there are already people there. That creates conflict. So movement of people associated with this equation is a vital part of the potential geopolitical upset as we move towards the middle of the century. So the problem, population distribution, doesn't match where the water supply is, and in fact we're already faced with problems associated with that. What about energy? Well, in the first instance, if we look around here, the R over P is the amount of available resource, and P would be in terms of current rate of usage. So if we take oil, for example, we're saying at the present rate of world usage, we've got about 40 years of oil remaining. These are figures not from any academic, but from BP. If you look at the Exxon figures, they would say about 50 years. But let's not argue about the number of years here. Please note that the figure includes conventional oil, oil that's yet to be discovered, and unconventional, for example, oil shale, which the Canadians have an awful lot of. So in terms of oil, likely that we're going to again hit the bumpers before mid-century. Is that a challenge? Not really. If we look at coal, we see that actually there's considerably more than 200 years of coal there. Many estimates indicate at the present rate of usage that's more like 1,000 to 2,000 years of coal left. So why is that relevant? Well, back to Africa. In South Africa, when they were threatened with an embargo on oil, they developed the so-called Sasol process, oil to petrol, and it's still up and running. And as a matter of fact, at recent oil prices, the Sasol process became competitive. So the technology's there. As this stuff, the oil, starts running out, so the technology for converting that to petroleum products will be developed and will become competitive. So that's not the real challenge. Gas, 67 years sounds like a better timescale. However, the growth in rates of gas use around the world is very considerable. The demand on a few countries that are big suppliers is a real worry in terms of security of supply for many countries. And of course for the United Kingdom, because the North Sea source of oil and gas is now beginning to run out, and running out more rapidly than we had anticipated, we're moving into a situation where we become net importers. We've already moved into that situation, and so we're looking now very keenly at this issue. So in terms of fossil fuels, resource, not actually the really challenging problem as we move forward in time. Infectious diseases, back to Africa. The challenges from infectious diseases are manifold, not least from the globalization of our economic system, which has led to much more diffusion of populations, and of course much more movement of individuals associated with that economic globalization. So a disease generated today anywhere on the planet, if it is going to spread, is likely to spread to the rest of us fairly soon after that. So we have a single concern in all countries about the spread of disease, and as that population grows and as the climate changes, this is a challenge that we're going to continually be faced with. So once again, for science challenges, this remains one of the big areas of challenge. One of the things I have been developing in government is a foresight program. I run the government's foresight program. This is an in-depth process in which we carefully choose a topic, in this case, detection and identification of infectious diseases. We work with usually 100 scientists, social scientists, economists in the area. In this case, we worked with 400. This was by far our most ambitious project. And we worked for two and a half years on this project with those people. The output led to the declaration at the St. Petersburg G8 meeting of heads of states. So the output from this program was bought by all of the heads of the G8 states. what were the important outcomes of this process? This was the first time an analysis had been done globally of animal, human, and plant diseases together. And for example, one outcome from the research was 80%, roughly, of human diseases derived from animals. It becomes critically important that we do more research which pulls together the plant, animal, and human disease process. Another outcome of that was, you might recall that we had a foot and mouth disease epidemic in the United Kingdom, and I found myself in the hot seat during that process. And we developed computer programs. For those of us who are surface scientists, this looked very much like surface diffusion that I had worked in before. There was a team from Imperial College, a team from Cambridge, and a team from Edinburgh who did the modeling for us. And an outcome was that we actually turned a rapidly expanding epidemic. Within 2 days, we turned exponential growth into exponential decay using a new control process. But what was on the top of my wish list during that epidemic? It was a device that would have looked like this and had many of the properties of this, but with a DNA chip at the end that you could stick into the orifice of an animal, the mouth, let me be more polite, of an animal, and within 2 minutes, PCR for example, you could have an analysis, does this animal have foot and mouth disease? Then you push your button, use the satellite, send the data to the map, the live map that we would have in Cobra in London, and we would see where this epidemic was spreading in real time. We fed this into our computer programs as part of this foresight analysis. And with this device, instead of costing the country £7 billion, this is the same size of epidemic, our estimate was about 50 million. Right, so one piece of technology, had it been available to us, could have totally transformed our ability to bring that epidemic under control in a much cheaper way. Roll this device out and look at, say, the current potential for a flu pandemic around the world. What we want to know is, where does that H5N1 virus transform itself into something that becomes a human-to-human virus? Where does that happen first? Because if we knew where that happened, we could move in with all our antivirals and attempt to quench it right there where it's being initiated. I've been over to the WHO. They have this big live map of all the epidemics developing around the world. And it's quite clear that if we could saturate the system in Southeast Asia and in much of Africa where the disease is present amongst poultry, if we had such a device, we would have a chance to quench an epidemic and probably prevent many, many millions of people of dying from an epidemic. So once again, I just want to stress, it's technology that can provide massive opportunities as we move forward to tackle some of these problems. Now, one of the difficulties, we might see this as an advantage, in all of this is a factor I've already referred to. It's the disparity in strength of science, engineering, medicine, technology around the world. So if you look at the map here, I'm plotting citation intensity on the vertical axis. Citation intensity is what? Citation per unit GDP. It seemed fair that I ought to divide it by something that was a measure of the size or economic strength of the nation. And along here, the wealth intensity, which is simply the GDP per person. This is a simple measure, per PPP if you're interested. And basically what you see is quite surprising when you do that. The US is not the top of the list, but the UK in terms of large countries is, with the small northern European countries and Israel ahead of us. Actually, if you add the citations output from all of the small northern European nations together, it equals the citations output from the United Kingdom. And the United Kingdom, in terms of volume of citations, not normalizing to anything, is second in the world to the United States. So we historically have retained a very strong position. Now, I'm going to reanalyze this next year, but you'll see that China, India, South Africa is the only country in the African continent that even appears here. Despite vast investment, in terms of citations, the analysis would indicate that those countries have got a long way to go. Another way of putting this is the great strength that we have in the UK is because of our 400-year legacy in science and technology. We have tremendous wealth in terms of not only human capital and being able to pass it on, but all of the infrastructure that goes with that. It does take a long time to build up. Now, those disparities place an enormous weight on us to see that we are looking at global problems. And that's really the main point I wanted to raise there. Now let me come to the atmosphere. Over the last 50 years, there's been much more attention placed on the quality of our air. Anyone who was in London in the 1960s, when I first came to Imperial College, will know that in the early 60s we still had smogs. And if you ever walked in a smog, you would know you could not see more than one pace ahead of yourself at a time. It was pretty scary stuff. We have now cleaned that up. It was a simple piece of legislation to understand that incomplete combustion generating small nanoparticles of carbon was the major source of that problem. We had acid rain. We introduced through the United States, and I want to stress, the US introduced a cap and trade process that finally got rid of sulfur dioxide emissions and solved the acid rain problem. So we have been cleaning up our air. The latest technology, for example, in terms of what is in a car. The most expensive single item in a car is the car exhaust catalyst. And it's a very sophisticated device. So if we took the latest diesel exhaust catalyst system, which contains a trap and produced by Johnson Matthey up in Royston, if we placed a diesel engine in here with that exhaust system on it, we would be cleaning up the air in this room. And that's a massive advance. I think it's a wonderful piece of technology that goes into the back end of your car. It requires that the car has a very sophisticated computer system in order to deal with NOx, CO, unburnt hydrocarbons, and these carbon particles from diesels. All of that's now a cracked problem. So we are cleaning up our atmosphere remarkably well. And mainly it's because we've paid so much more attention to it, probably driven by Los Angeles and San Francisco being in such a terrible state that they really had to lead the world out of that problem. Amongst all of this, however, we've left ourselves one problem, and that is, of course, that we are still emitting carbon dioxide. So, of course, that very sophisticated car exhaust catalyst that I've just referred to does not catch any of the carbon dioxide. In fact, carbon dioxide is one of the products that the catalyst is converting the noxious gases into. So we come to the Earth's energy budget and the question of global warming. Here I'm just pointing to a figure that is really rather old-fashioned in the sense that it goes back to essentially to 1827 when Fourier decided that the business of calculating the average temperature of the Earth was within his grasp. He said something very simple. We've got incoming solar energy. That's providing heat for the surface of the Earth. We've got outgoing radiated energy. That's going out into space. Since the Earth is no longer effectively heating up, it's in steady state, those two must be equal. But in order for them to equal, it means that the land surface temperature must have risen until the radiated energy was equal to the solar energy coming in. And although he didn't have a T to the 4 power in mind at that time, he knew that the radiated energy was a very sensitive function of the surface temperature. So he thought, I can calculate that temperature accurately. And he calculates it, and he gets a number of around minus 20 degrees centigrade. And a good theoretical physicist might have published that. But he realized, John Pendry is here. But he also remarked on something else that he saw as a problem. What happens if I switch off the sunlight? That vast amount of heat that's arriving on the planet is still equaled by the vast amount of radiated energy going out into space, so the surface of the Earth must cool down very rapidly. So he calculates that over 10 hours finds that the surface would cool another 20 degrees. So daytime, nighttime temperature differences should be big. And of course at this point he realizes he's left something out of the physics, and the something is the blue stuff here. So he had calculated the properties of the moon, and when he now takes the atmosphere into account, and this really is like a good theoretical physicist, he introduces a Fourier coefficient. And his coefficient is simply the amount of that radiated heat that is absorbed by the atmosphere. He didn't know how much it was, so he puts in an alpha function. And of course he then comes out with the right average temperature of 15 degrees centigrade. But what was clever was that now his daytime, nighttime temperature difference was relatively small. So he published it. Then we move on to the British scientist Tyndall. We get to experimental physical chemistry now, if I may sell the subject. And what Tyndall says is, well, I'm going to check Fourier's coefficient. So he sets up a tube, and he, being a very careful scientist, he removes all of the impurities from the air in his tube. So he removed all the carbon dioxide and water vapor, and he measures the coefficient, and he finds it's 0. So Tyndall did the critical experiment. He then repeated it with air as it is, and he found Fourier's coefficient very accurately. So what he had discovered was that the majority of our atmosphere, nitrogen and oxygen, don't absorb any of that radiated energy, and it's the minority gases, carbon dioxide and water vapor, that were doing it. So greenhouse effect, Fourier. Greenhouse gases, Tyndall, 1860. None of this is modern science, as you can see. We now have reached the point where another scientist says to himself, well, I should be able to calculate what would happen if we were to burn so much fossil fuels that we should change the average temperature of the Earth by putting too much up in the atmosphere. His name was Arrhenius. And he's a bit of an icon to physical chemists. Arrhenius, Nobel Prize winner, 1903, 1896. He just used Tyndall's coefficients, Fourier's equations, and he calculates the temperature of the Earth would rise by 5 degrees centigrade. Now we have, back in 2001, I was in Japan, and I brokered a deal where our scientists could use the Japanese Earth simulator, which was just coming into being at that point. And with the biggest program in the world on this, in which volcanic activity, this green stuff down here, the changes in solar energy, everything is put into this, and the answer is 5 plus or minus 2 degrees centigrade. So basically what we would say is that Arrhenius had got the physics right. That's not to say that there aren't big issues in the current calculations. One issue is that white cloud on the left. What's the function of clouds? Well, we know the function fairly easily at night because there's no solar energy coming in, so it's all a matter of keeping the radiated energy in so that the clouds act as a blanket. What's the function of a cloud during the daytime? Well, if the cloud is a nice little white one like this, it's going to reflect some of that sunlight straight back out into space. Now you've got a much more difficult calculation on your hands. If it's a dark cloud, it won't do that. So it's a more challenging process. Now, of course, what is also challenging about that is that as you raise the carbon dioxide level in the atmosphere and the temperature starts rising, the ocean temperature goes up, and using Clausius-Clapeyron's equation, you then know that the water vapor pressure goes up. Big positive feedback term, that pushes the global temperature up, but what also happens to cloud formation as you increase both the atmospheric temperature and the amount of water vapor, another big challenge. And then finally, the challenge is on aerosols. We have produced a lot of man-made aerosols, and in that process, we've mainly been producing material up there that reflects sunlight back out into space. So aerosols have a cooling effect. If we stop producing aerosols altogether, it's likely that global warming will accelerate, therefore. So that's another difficult part of the calculation. But nevertheless, the physics, as I say, is basically there. Now what have we been doing? The amount of science that comes in this field weekly is simply phenomenal. And I'm showing you some very recent data. When I started talking about this, I used to go back 200,000 years and then 700,000 years, a giant step, when an ice core from Antarctic was taken, which was 3 kilometers long. At the bottom was a snowfall that had occurred 800,000 years ago, and then at the top you've got the snowfall that fell last year. So you had a record of the Earth's atmosphere over that time scale. And the data for that is shown in the bottom slide just for the last 400,000 years. But look at the data in the top slide. Ocean sediments are yielding even more. And by the way, the matching of ocean sediment data and ice core data is really pretty good. And you see, going back in time, we can get to the point, the Eocene, Pliocene era, when 50 million years ago there was no ice left on the planet and temperatures were very high. We're here using oxygen-18 isotopes as a proxy for temperature, but temperature is going up on the vertical axis. And you'll see that 55 million years ago we have a maximum in the planet's average temperature. And as we come forward in time, it's taken about 50 million years to cool down to a reasonable temperature. And we come into these oscillations, the glacial interglacial periods. So that's not noise as we go into the last 2 million years or so. That's the development of the glacial interglacial. And in the bottom slide, we're just showing the same information now spread out over 400,000 years. And so these are the glacial periods, the ice ages, the warm period relatively short, and so we have this repeat process of warm periods. And this is the current interglacial or warm period. And what is important, of course, here is to recognize this is 18,000 years ago, 12,000 years ago. We get into our current warm period, it's remarkably stable, rather different from previous warm periods, and thank goodness for that. But there's now a real question, is that because we started entering an Anthropocene period rather earlier than we had thought? In other words, is this earlier change here, we might have expected this to return to a glacial due to our change in land use. So when we focus on carbon dioxide production, we've got to remember that as we chop down the trees and reduce the greening, we're going to see higher carbon dioxide levels. So there's a question as to whether we actually entered the Anthropocene as we changed land use. This is the period of our civilization. On the upper curve, you see the correlation between carbon dioxide levels and temperature. The red curve is the carbon dioxide levels, and we know that for the past millions of years, carbon dioxide levels have been remarkably constant in our atmosphere between 190 parts per million and 270 parts per million. And when it's high, we have a warm period, and when it's low, we have a glacial. And so what we have is Fourier's effect in demonstration here. And then we discover all of those fossil fuels and we start burning them like there was no tomorrow. The rate of burning, so this is the point of the Industrial Revolution. Put it all down to those guys up in Liverpool and Manchester. And we start burning fossil fuels and mining for them. We become more and more effective at mining for them. And the carbon dioxide level has risen at a rate that is quite unprecedented. So I think I've got here the latest data point, which is 383 parts per million, and it's rising at 2 parts per million per annum. So we know we're going to pass 400 parts per million in less than 10 years' time. Right, so remember, Arrhenius's calculation was for doubling, which would have been about 520, 540 parts per million. We are certainly heading towards that figure, and by the end of the century, we could easily reach 750, 800 parts per million. You want to go back on, on this top curve, you have to go back quite a while. Never mind these oscillations, you've got to go back quite a while before you get to a carbon dioxide level that we're already at. And of course, that's quite useful. We've just got to recall that past planetary behavior could be repeated. So there's a real question. I think I know the answer. Have we actually switched off these oscillations and entered the first hot period since we were back up here? And if we then raise that question, we're asking the question that the political system is now aware of and is now discussing in some detail. What are the impacts likely to be of that rapid rise in carbon dioxide due to our change in land use, but also critically due to our use of fossil fuels? Methane is a very important greenhouse gas. Because animals are a big part of our method of providing food, methane has also risen with population growth. So those are the other forces of the climate system. So this is what's happened. If we look at the observed average global temperature in red, this goes back to 1863 when the British Met Office began collecting data from 300 weather stations around the Earth. And just taking that data forward, we follow the red lines, and we see that the temperature has now risen from the pre-industrial period by around 0.7 degrees centigrade. What's played over this is the Hadley Center model, which is now being played on the Earth simulators I've described. They run this model, of course, forwards to try and predict the temperature change, and then run it backwards to see how well they can describe previous behavior. If scientists who work on this are challenged to say, but you must have put some fitting parameters in, they go quite apoplectic. And the reason is their models are so complicated. They say they wouldn't know what parameters to pull around to try and make it fit like that. This is a pretty good description of the planetary climate system. And the Hadley Center here in the UK is certainly the leading modeling center in the world. You may ask, why have we done so well in Britain? Well, that Hadley Center is part of our Met Office. The Met Office is in the Ministry of Defence. That, if you like, has guaranteed that it would be reasonably well funded. But why in the Ministry of Defence? Well, actually, it's not just that the British like talking about the weather. We're a maritime nation, and we depended on the weather. Knowing which way the wind blows in a battle at sea was absolutely critical. And so our entire history has developed around the weather. And being able to forecast the weather was always seen by the British to be a very powerful tool. Forecasting became tomorrow's weather, next week's weather, 3 monthly forecasts, and before long you were into climate prediction. And that's where the Hadley Center came into being. Now, if you take the Hadley Center models, you've really got to be asking yourself what happens ahead of this time. Remember that I'm saying the models predicted this piece of increase here. So this doesn't look too bad for a prediction. And we now move forward in time. And we're now seeing the Hadley Center run large numbers of models with different physical parameters and conditions put into them. And they're producing these probability analysis curves showing that if we were to arrive at a 450 part per million asymptote for carbon dioxide in the atmosphere, the ultimate temperature rise of the planet would reach around 2.2 as the most probable temperature rise. But in the 5 to 95% limit, you're talking about 1.6 to 4 degrees as the sort of range that we need to be preparing for. That's at 450, and I've just told you that 400 we're going to pass in less than 10 years, and the 400 did not include methane gases and other gases. We're certainly, in my view, unable to stop our greenhouse gas level such that we can keep on the blue curve, and we're more likely to be politically capable of managing the 550. At any rate, what I believe we should be doing is aiming to be as close to the 450 as we can get. If we exceed 550, it's already becoming apparent that the global consequences become catastrophic. But let me just tell you, this is the ultimate temperature change. There is a lot of inertia in our climate system. You could count it as in decades, roughly 3 decades of inertia. In other words, carbon dioxide level is rising so quickly that if we were to terminate now and keep it at 383 parts per million, the next 30 years of global warming is already in the pipeline. It would hardly make a difference compared with business as usual. Any advantage is going to only appear in later years. Why do we want to avoid this problem? Well, we're heating the oceans, as I've said. Ocean expands as it's heated, and as it expands in a confined area, it has to go up, and so ocean levels rise. What I should have said to you before was that between an ice age and a warm period, temperature differences around 5 to 8 degrees centigrade, and over those differences, repeatedly, ocean levels change by about 120 meters. Now, if we lose all of the remaining ice on the planet, sea levels would rise another 110 meters. So we are talking about very substantial amounts of ice, and if you couple that in with warming, it would be about 110 meters. So if we just go on to the year 2080, you can see that vast coastlines of our planet come at risk. Now, the important point here is that we have always treated our planet's geography as a stable feature, because during the period of our civilization, we have not seen a significant temperature change, so we have assumed that the geography is unchanging, essentially, bar a few volcanoes. And therefore, we've grown most of our cities at coastlines, our major cities. 80% of our population is at the coastline, which means that a very significant number of people are at risk as sea level rises. And this simply indicates business as usual. We have hundreds of millions of people having to be displaced from their place of abode. I stress that this is going to happen relatively slowly, and so they won't just wake up one morning and find the water is up to here. But nevertheless, the economic and political consequences of this are massively destabilizing to the world economy. So that's one feature. The good news on this slide is that if we manage to control this, such as we stabilizing at 550 parts per million, then we can reduce the problem by quite a large amount. So the blue indicates that 80 to 90% less people would be displaced from their place of abode. Now, what about the UK? I set up a foresight project looking at flood and coastal defence attack for the UK. Actually, the project was initially, when we scoped it, to look at the impacts of climate change for the United Kingdom, and it's flooding that is our biggest problem as we move through this century. And this is the outcome of the analysis. Now, we have to play into different scenarios because we can't predict whether we're going to have global good behavior on emissions or bad behavior. So these are the extreme scenarios we calculated for. This scenario is business as usual, keep emitting carbon dioxide. This scenario is where we're limiting carbon dioxide to that 550 parts per million level. Now, when you play this forward in terms of cost of risk of dealing with the risk, then it's very, very clear which scenario you'd rather be on. When I first presented this in the House of Commons, I was asked please not to publish it because we're on a sufficiently small pixel scale that people would pick out that their house in my constituency was at risk. Now, what I had to point out is that this was going forward in time without a change in government policy. And so what we did in that foresight program was advise government on what action is required to keep the map yellow as we move forward in time. So we have proposed a risk and flood defence management scheme, which has meant that the government has increased expenditure in this area from £200 million in '98 to £500 million a year now. And so let me reassure you, the idea is to keep the map yellow. But in that process, and by the way, you'll see flood risk is not only at our coastlines, it's also our cities. And the reason it's in our cities is because we have a drainage system and, dare I say, a sewerage system, and the two, wisely or not, connected by our Victorian forefathers. They were designed for a period when rain in Britain meant that sort of drizzle stuff that comes occasionally and rather softly. The floods that we are already beginning to see as flash floods in our cities can't cope. We can't cope with torrential downpours. And so what is required to avoid flooding of cities of the kind shown in many of the conurbations here, those floods would need to be handled by modernizing the drainage system, but also by creating nearby flood plains. You need to run the water away rapidly into floodplains. This has massive implications for planning permission, because otherwise your house, of course, is going to become not only wet but also uninsurable. If you were on this right-hand scenario, as you might imagine, it gets very, very expensive. So at the moment we're planning to be on the left-hand scenario. And if there was anything that persuaded the British government that I should try and persuade all governments that we should try and control emissions, it was the outcome of this report. It's just looking at the cost of dealing with the impacts of climate change. And in Britain, the costs are actually relatively small compared with other countries, and we have the wealth and capability to manage it. What is the biggest problem that we face that we would like to avoid? As an experimentalist, I do like to test theoretical models, but let me say this is an experiment I'm suggesting we don't do. The icon of what we should avoid has become not melting all the ice on Greenland. If we only melted the ice on Greenland and didn't take account of warming ocean or any other ice melting, the sea level rise would be 6.5 meters, about 20 feet. So certainly London becomes unprotectable at that sort of level. So there's the icon of what we should avoid if you don't want to test the theory and would rather protect cities like London. By the way, Venice, of course, is the first city to be lost. Half of the problem in Venice so far has been from Venice sinking, and the other half is from the sea level rise that is already occurring. But as time progresses, it's going to be the sea level rise that will finish Venice off, unless something very dramatic is done. So the Hadley Center tried to model the melting of ice on Greenland. There's this mass of ice, and they modeled it, and I'm sure theoreticians can do better than this, but it's rather like a big chunk of ice that you take out of a fridge and you put into a warm room. It melts very, very slowly. And when they ran this model forward, it took about 3,000 years for it to melt, with carbon dioxide levels well over 550 parts per million. Now, even on a shorter time scale, partial loss of Greenland is a major problem. But nevertheless, if you actually look at the way the ice on Greenland is already melting, and it is melting much more quickly than the models predicted, you'll see that it's not following the theory at all. So these moulins, this beautiful picture that Roger Brathwaite from Manchester University took is just an example of a moulin. These rivers that start forming during the summer melt and then start forming waterfalls which penetrate right down to ground base and start lubricating the ice between land and ice, lubricating the interface, and so you get premature calving. You get icebergs forming from the land. So there is a much faster loss of Greenland ice already than any of the models predicted. The most recent analysis, I think I might have it here, published just about a month ago in Science. There are 3 satellite measurements made. This is easily, for me, the most fascinating. It's a measurement of the change in the gravitational field of Greenland due to the loss of ice. And this shows that it's losing ice at about 200 cubic kilometers per annum. But the analyses indicate a range of about 120 to 240. There's an altimetry analysis and 2 gravitational field analyses. Now, the anticipated figure was around 60 to 80 cubic kilometers per annum. So these figures are already looking a little alarming, but they also match up with the satellite photography of Greenland, which is indicating that these moulins that I showed you are having quite a dramatic effect. So the answer is to the question, we don't know what level of carbon dioxide would lead to irreversible melting of Greenland, if indeed we haven't got there already. And so preparing for the impacts is what we need to be working on. Dealing with the impacts, as with the Flood and Coastal Defence Management Programme in the UK, is critical for all countries, and it's got to be done country by country. So far, we are the only country that's done it, but we've now taken our foresight team out to China, and we're working on the Yangtze Basin area with the Chinese government. The Chinese government is also getting a little alarmed about the impacts of climate change as a result of the output of that model. What we really need to do is to get global agreement on a solution to the problem. Kyoto proved to be unacceptable. Now, I just put this curve up as an indication of the extremely tough nature of those negotiations, which I am involved in. The United States leads the world in emitting carbon dioxide, measured as tons of carbon per capita. That's about 5.7. And at the other end of the spectrum is India at about 0.2. And Europe, Western Europe, is there at about 2.4. Now, if you get all of those countries represented around a negotiating table, the starting point is so dramatically different that it's very, very challenging for each country to look at a single solution and say that's equitable to us, and it's also equitable to everybody else. That's the nature of the political challenge we're faced with. And I certainly think this is the biggest challenge civilization has ever had to face up to. It's a big challenge for 2 reasons. One is, can we meet it using alternative technologies and more energy efficiency gains at the same time as much of the emerging world wants more energy usage? Can we manage that technologically? But secondly, can we get politicians to make a decision that won't have any impact not only in their own term of office, but even for the next 30 years? Because the only return is going to be in the period 2050 to the end of the century. So it's a massive challenge, and I do think we're beginning to see a bit of a turning point. There's where we want to be. This is emissions per capita, emissions per annum, so the rate of emissions, and the blue curve is business as usual. That's the curve we're on now, and with increased energy demand around the world, that curve is turning upwards. If we wanted to be on the 550 part per million trajectory, the yellow curve is an approximation to getting there, and the red curve shows the very challenging process of getting it down to 450. Now, I would love to be on 450. I don't want to be misunderstood here. In fact, I would love to be at 270. But so the question is, how do we achieve that? And even if we're on this red curve, as I've said, dangerous climate change is already with us. We will have to deal with the impacts of climate change as we go forward. The Stern Review has emerged. It's the first detailed economic analysis from a world-leading economist. Stern was previously chief economist at the World Bank, has a long and sustained academic career, and is now chief economist in the Treasury. And his conclusion is that if we don't deal with this problem, we are storing up an economic collapse that would be at least equivalent to the 2 world wars and the Great Depression in the first part of the 20th century. And this is natural consequence of the things I've been describing. But the other thing he's saying, and this is very important, the cost of action in all of his models, and he's using classical models and just basing it on the best science. He and I have been working closely on this. The cost of dealing with it is relatively small. So the integrated loss of GDP growth by 2050 would be an estimated 1% plus or minus 2. In other words, some of his models show that with the increased investment in alternative technologies, the increased employment, he actually gets net economic growth of around 1%. So it's not a big cost. You would say a no-brainer, but I just remind you, the cost comes in the next 30 years, the benefits come in the later part of the century. What are we doing as a government? During our G8 presidency, the Prime Minister put climate change and African development as the 1 and 2 items on the agenda and nothing else. I do believe that that has meant that this topic has risen to the top of the agenda in countries around the world. The announcement by John Howard on Monday last week, John Howard, Prime Minister of Australia, that Australia would now need to be looking at carbon trading, a fiscal process to drive down carbon dioxide, means that this has now been taken seriously in countries where previously there has been tremendous resistance to the idea. So the Gleneagles process has now turned into a dialogue. We met in Mexico last month, and I felt rather buoyant after that meeting. 20 nations sitting around the table, the top 20 world economies, but including China, India, Mexico, South Africa, the countries that the Prime Minister invited to Gleneagles, including those countries, and agreed the science is in. The economics is looking very promising. We had reports backing Stern from the International Energy Agency and the World Bank. And then we started discussing the political process. How do we find that equitable solution that every country can walk away with and say, I can sell this to my population because it's dealing us well. That's where we are now. The Gleneagles dialogue is, in my view, an excellent way of breaking the morass that we've got into in the political discussion, precisely because those leading 20 nations could come up with a solution which we can then take to the other 163 nations at the United Nations Framework Convention on Climate Change. In that bigger meeting, it's really very, very difficult to find a solution. So that's where we are now. We must adapt as we move ahead, and we have to also reduce our dependence on greenhouse gases. How do we do that? It's science that is pointing to the potential problems ahead of us, and it's technology that's going to provide the solutions. Here in the UK, two of us, Paul Golby, Chief Executive of E.ON UK, and myself, have set up an Energy Technologies Institute. It's backed by the Chancellor to the extent of £500 million, and we're raising the other £500 million from the private sector. In addition to the companies shown here, BP, Shell, EDF, and E.ON, we also have now Rolls-Royce, Scottish and Southern, and several others who haven't quite signed on the dotted line. By mid-December, we'll have the 10 board members that we want paying the other £500 million over the next 10 years to get this fully established. I think that this indicates that the UK is serious about moving ahead, and we're moving ahead with major multinational companies. The President of the EU, Barroso, came to see me to ask for a briefing on this. he's quite interested in this rolling out as a European-wide venture. We're going to set it up in the first instance as a UK-based venture, but we're certainly very open to it becoming a multinational venture. So I think we've got a sustainable future. We have the science, the medicine, the technology to deliver. I believe the 9 billion population is not beyond us managing on this planet, but it does mean that we need to take a different approach to science and technology in the 21st century. I think instead of continuing to develop the gizmos that have given us such a pleasant life in the 20th century, we now need, in addition, to focus on the various problems that I've mentioned here, but in particular, the question of sustainably living within the resources that the planet offers. I see that as the key 21st century challenge. Thank you.
You've been listening to a special lecture vodcast from Imperial College London.